Continuing our exciting, thrilling, action-packed lecture of 1.3, new functions from old functions. This, of course, is when the old functions that like to listen to classical music and just sip on coffee give way to the new functions that like to skateboard and drink Mountain Dew. We're going to look at some algebra of functions, combination of functions mainly, and what we mean by that is just doing some algebraic operations on these things, adding them, subtracting them, multiplying and dividing them. We can do that to functions just like we can do it to numbers. And we do it piecewise, basically. What we mean by that is, or pointwise I should say, f plus g of x is equal to f of x plus g of x. In other words, if you want to take a new function called f plus g, you can find that new function at a particular value x by taking the old function f at that value x, the old function g at that value x, and adding the results together. So this is pointwise definition of the algebra of functions. In the same way, we define f minus g of x to be the function evaluated at x, the function f evaluated at x, minus the function g evaluated at x. If we have a new function called f times g, and we want to evaluate that at x, we take the function f evaluated at x and multiply it by the function g evaluated at x. In other words, we take the operation pointwise, and finally for division we take f divided by g of x, and that equals f of x divided by g of x. So it's pretty simple, actually, the algebra of these functions. The thing we want to look at is the domains of these things, and again, this is all in a table on the bottom of page 42 in your book. And so if we say that the domain of the original function f is a and the domain of the original function g is b, then you can look at the domains of these functions, and for the domain of f of x plus the domain of g of x, well, the domain of f plus g of x is going to be the intersection of the two original domains. And that's going to be the case all the way on down. We just take the intersection of the two original domains to get the new domain of the new function that we got with one of the algebraic operations of addition, subtraction, and multiplication. Now, for the last one, though, the domain is going to be, well, we can take everything, all the x's, in the intersection. So it is the intersection as long as our function g is not equal to 0. So when we're doing division of functions, so function division, we have to make sure we don't divide by 0. So any value of x that makes g equal to 0, even though that was in the original domain of g, it's okay if the function g comes out to be 0. But if g is in the denominator of a rational function, then of course we can't have that denominator come out to be 0. So the domain is the same. It's that a intersect b, only we have to throw out any values of x that make that denominator 0. By way of example, let's take a look at number 32 out of your textbook. We're given two functions. F of x is the square root of 1 plus x. G of x is the square root of 1 minus x. We want to find f plus g, f minus g, f times g, and f divided by g and state their domains. To do that, the first thing you're going to want to do is find the domains of the individual functions. Let's start with the domain of f. Now here we have a square root, and so what we need to make sure is that what we're taking the square root of, 1 plus x, is always at least 0 or positive. Let's see, if we subtract 1 from both sides here, we get that x is greater than or equal to negative 1. So our domain for f, written in interval notation, we could say, is everything from negative 1 on up to infinity, always an open parenthesis around infinity or negative infinity. Let's look at the domain of g. Here we have a similar situation. We have a square root, and so we need to make sure that what we're taking the square root of is always positive. Here, let's go ahead and add x to both sides, and we get that 1 is greater than or equal to x, or x is less than or equal to 1. In interval notation, that's everything from negative infinity on up to and including 1. Alright, so look where these domains intersect, because remember the domain of the functions when we combine them is going to be the intersection of these two things. We have 2 points we care about, negative 1 and positive 1. The domain of the function f was everything from negative 1 on out to infinity. So that was this domain right here, with including that point negative 1, while the domain of g was everything from negative infinity up to and including positive 1. So you can see where these two domains intersect is in this interval between negative 1 and 1. So if we call this a and we call this b, we can see that a intersect b is equal to the interval from -1 to 1. So that's very important to establish before we start looking at the combinations of these functions, which we will do right now. Let's look at part A. We want f plus g, a new function f plus g. Well, our formula says that's just going to be f of x plus g of x. And so we're just going to take the formula for f, it's the square root of 1 plus x, plus the formula for g, it's the square root of 1 minus x, and that's it. We can't combine those two terms. So there's our formula. The domain is, like we said, A intersect B. It's -1 to 1. Alright, let's take a look then at part B. Part B, we want to take, let's do that in purple maybe, f minus g. What's going to be f of x minus g of x. And so that's going to be the square root of 1 plus x, that's the formula for f, minus the square root of 1 minus x, that's the formula for g. Alright, what's the domain here? The domain of f minus g is going to be the same thing, the intersection of the two domains, which is from -1 to 1. Let's take a look at part C, where we're taking f times g of x. We can either write the argument, the f times g of x, or just leave it like f times g, but it's going to be f of x times g of x. Well, let's see, that's going to be the square root of 1 plus x times the square root of 1 minus x. Now, if we take the square root of 1 plus x times the square root of 1 minus x, we can write that as a single square root of 1 plus x times 1 minus x. And if we FOIL that out, we get the square root of 1 minus x squared. And again, to make sure this stays positive, we would have to have that same domain. The domain of f times g is going to be that same thing between -1 and 1. You can see if we let x get bigger than 1 or less than -1, x squared would be bigger than 1. 1 minus that would be a negative number, and we would not then be able to take the square root of that negative. Finally, let's look at part D, where we have f divided by g. F divided by g of x is equal to f of x divided by g of x, which is going to equal to the formula of f, which is the square root of 1 plus x, divided by the formula of g, which is the square root of 1 minus x. Now, what's the domain here? Well, the domain here, remember, is the intersection only. You have to throw out any values that make g of x equal to 0. Well, we know that g of 1 is equal to 0 because g of 1 is equal to the square root of 1 minus 1, which is the square root of 0 or 0. So we have to throw that out of our domain. So the domain then of f over g is going to be, well, it's that intersection between -1 and 1 minus that point 1. So it's just going to be -1 to 1, only an open parenthesis around that 1. So it's the intersection of A and B, the domains of f and g, but take out that point that makes our denominator function equal to 0. There's only one point where g of x is equal to 0, and that is at 1, so we take that point out of our domain. Finally, the last topic in section 1.3 is composition of functions. Let's suppose we have a couple of functions. Let's let f of x equal x minus 3, and let's let g of x equal x squared plus 2x. Let's suppose I want to find f of g of 2, say. Well, what does this mean? That means I'm going to work from the inside. I'm going to find g of 2 first. So let's go ahead and do that. G of 2 is equal to, let's see, according to our formula, it's 2 squared plus 2 times 2. That's 4 plus 4, or 8. So I'm going to put the 8 in for g of 2, and then I get f of g of 2, which is equal to 8. Well, f says to take the function, take the value you put into it, and subtract 3. So we get f of g of 2 is equal to 5. Now, what happens if I take g of f of 2? If I go in the opposite direction, g of f of 2. Well, here I'm going to work from the inside again. So we're going to take f of 2 first. F of 2, according to the formula, is 2 minus 3, which is -1. And so g of f of 2 is going to be g of that -1. What does that equal? Well, g says to square that plus 2 times that amount. So we get -1 squared is 1, plus a 2 times -1 is -1, which is 0. Notice we get two different things when we take f of g of 2 and g of f of 2. Well, we have a name for this when we take one function, evaluate it, and then put the result into a different function. That's called the composition of functions. So if we take f composed with g of x, that's equal to the composition of f with g. And the formula for finding f composed with g of x, we have a new function called f composed with g. This is a circle here. It's an operation. The composition, the notation for that is just a circle. It's not the letter O. It doesn't spell fog, even though we kind of call it fog sometimes. F composed with g of x, that means to take f of g of x. In other words, evaluate the function g first at a particular point. When you're done with that, put that result into f, just like we did before. Now we can go the other direction. We can take g composed with f of x, g circle f, which is the composition of f with g. Or I should say the composition of g with f. And here, what we get is g of f of x. As we saw in that last example, the order does matter. Some operations, the order doesn't matter, like addition or multiplication. It doesn't matter which order you add two things or multiply two things, and that includes functions. But this operation for functions called composition, the order does matter, as we saw in the last example. When we took f of g of 2, which we could say is f composed with g of 2, we got 5. When we did g of f of 2, which we could say is g composed with f of 2, that's what those are equal to, we got 0. So we got different results depending on the order in which we compose the exact same functions at the exact same points. Now we can find formulas then for f composed with g in general terms. If we look at our two functions again, f and g, we can find the formula for f composed with g of x. This is a new function we're finding, and we're going to do it by taking f of g of x. Well, that means we're going to take the formula for g and put that into the function for f. So we're going to be taking then f of x squared plus 2x. What does that mean? Well, it means, again, we're going to take this whole formula, x squared plus 2x, and we're going to put that in wherever we see an x in the function f. Because when we take a value and put it into g, it comes out looking like this. It's the value squared plus 2 times that value. That's what we put into f. F says to take that and subtract 3. So we get x squared plus 2x minus 3. There's a new formula for f composed with g of x, that function. Now, if we find the formula for g composed with f of x, here we're going to take g of f of x. Well, what is f of x? F of x takes the original value and subtracts 3. So we're going to be taking g of the original value minus 3. Here we're going to be taking this formula and putting it in for x in the function g. So g says to take whatever you put into it and square it. So we have x minus 3 squared plus 2 times the quantity x minus 3. So let's go ahead and simplify this. This is equal to not just x squared minus 9 or x squared plus 9. Please don't make that mistake. We have to FOIL this quantity out when we square it. I'll go ahead and distribute this 2 through the second quantity to get 2x minus 6. FOILing this out, we get a first of x squared. Let's see, minus 3x and minus another 3x will be a minus 6x plus 9 plus 2x minus 6. And combining like terms, we get our formula for g composed with f of x. And it's x squared, let's see, minus 6x plus 2x is minus 4x. 9 minus 6 is 3. So x squared minus 4x plus 3. Notice that this formula here is different than this formula for f composed with g. And by the way, there's nothing that says we can't compose a function with itself. If I want to take f composed with f of x, that's f of x. That's f of x minus 3. And so I'm going to put the formula for f into the variable for f. Remember that in this case, f of x is x minus 3. So I'm taking x minus 3 and putting that in to x in my function for f. So I get x minus 3 minus 3, or x minus 6. So there's f composed with itself. Finally, let's look at an example or two. Number 44, you're given the function capital F of x equals the sine of the square root of x. We want to write this as f composed with g of x. Well, remember this notation, f composed with g means we're going to take f of g of x, that means that g is going to match up with our inside function. So I'm going to let g of x be the inside function here, the thing I would do first if I were evaluating this original function. If you were evaluating capital F of x, the first thing you would do is take the square root of the number, then you would take the sign of that. So I'm going to let g of x be the inside function. F of x then is going to be the outside function. F is the outside function, which is going to match up with sine. So f of x is going to be the sine of x. Now when we take f composed with g of x, that's f of g of x, which is f of the square root of x. F says to take the sine of whatever you put into it, so we take the sine of the square root of x, and we get the original function capital F of x. Finally, let's look at number 48. We have a function capital H of x is equal to the 8th root of 2 plus the square root of x. We want to express this as f composed with g composed with h, as a composition of three functions. Well, let's think about what that means. F composed with g composed with h is going to equal f of g composed with h, or f of g of h of x. So that means we're going to want h of x to be the inside function, then g, and then f. Well, we're going to define the inside function by what we would do first if we were evaluating this function. If you were going to put a number into the capital H of x function and evaluate it, the first thing you would do is take the absolute value of it. So let's let h of x represent that first thing, which is to take the absolute value. Now what do you do after that? After you take the absolute value, you add 2 to that number. So let's let g of x be the operation of adding 2 to what we have thus far. So it's going to be 2 plus x. And finally, after you've done 2 plus the absolute value, you take the 8th root. So we're going to let f of x represent that, taking the 8th root of what we have. Now if we take f composed with g composed with h of x, that's f of g composed with h of x, which is f of g of h of x, which is f of g of, what's h of x? It's the absolute value of x, which is f of, let's see, g of the absolute value. G says to take 2 and add it to whatever you put into it. So that's going to be 2 plus the absolute value. And now we're taking f of all this. Well, f says to take the 8th root of whatever you put into it. So it's the 8th root of 2 plus the absolute value of x, which is our original function, capital H of x. So there's composition of functions, and I think that should be enough information to get you going on your homework 1.3. The password you'll need to get into the 1.3 homework is Arcadia, which means a region of simple pleasure and quiet, as in the student wanted to find an Arcadia after listening to the 1.3 lecture. Arcadia is the word you need to get into 1.3. Please let me know if you have any questions.